Okay, guys, welcome to section 3 of chapter 6. This is the last section of chapter 6 and the last bit of information for you. So we know how to calculate velocity to figure out how fast something goes, right? That's something we've covered. But what about when different sized objects are traveling at the same speed? So imagine a car going 55 miles an hour versus a baseball going at 55 miles an hour, right? Both totally possible. So the motion isn't the same, right? It can't be the same. Now they might be going at the same speed, but there's something about them that's different, and that is momentum. Okay, so take a minute and come up with 5 things that have momentum and a list of 5 things that don't have momentum. And we'll check back in a second. Okay, so hopefully you thought of some things that have momentum. So some of these examples, obviously the things that have momentum, a bowling ball, right? So it's moving. It has both mass and velocity. Okay. How about a street sign? All right, so a street sign, sure, it has mass, but it's not moving, right? It's stuck on the ground, so it has no velocity, therefore it has no momentum. So those are sort of the kind of things you want to think about when you think about momentum. All right, momentum is, well, we'll talk about that in a second. So today we're going to calculate the momentum of moving objects, so we're going to do a little bit more math, and we're going to explain the law of conservation of momentum. So we should know from earlier in the year that the word conservation means to save or to retain. So there's this law that we're going to learn about that talks about how momentum is sort of carried over when two objects interact or crash into each other. So momentum of an object depends on the object's mass and velocity. So momentum is a measurement of moving objects that is the product of their mass and velocity. All right, so you can see that in the equation here. All right, so product, obviously, meaning multiplied, right? So when you multiply these two values, the mass and velocity, you can see the momentum. And momentum is usually expressed with lowercase p. Why? Well, we've already used m for mass, right? And for some other things. So p is what we're using for momentum. Okay, so momentum, as we've shown before, is a way of measuring how much motion a moving object has and how much force is needed to change that motion. Okay, so a car moving at 55 miles per hour has a certain amount of motion, right? So it's moving from one place to another. So it takes a certain amount of force to stop a car from moving that speed. Now, baseball, right, being a lot smaller, can also travel at 55 miles an hour, no problem. I bet I could throw it that hard. I used to be able to throw it back in the day. So the baseball travels at 55 miles per hour. It takes a lot less force to stop a baseball than it does the car. So I can catch a baseball at 50 miles per hour, 55 miles per hour, because it's got a low momentum. So despite its speed, I can catch it because it's got a low mass, right? However, I can't catch a car traveling at 55 miles per hour because it's got a lot more mass, right? So it's got a lot more momentum. Okay, so it's got more mass equals more momentum. So to calculate momentum, just pretty much the easiest equation you could do. Okay, take a second, look at the example here. We're just multiplying the mass here by the velocity. Okay, and notice the velocity has a direction with it, right? North. So obviously that separates it from just having a speed. So it's got to have a direction to it too. So we're multiplying 120 by 16, and your unit for momentum is going to be kilograms times meters per second north. So you're kind of just taking all the units and kind of mashing them all together. I'm not going to really ask you too often to give me that unit, so don't sweat it too much. Just make sure your answers here have both of those units. Okay, so there's two ways to think about this law of conservation of momentum. All right, so the one thing that governs all of this is when any two objects collide, the total amount of momentum stays the same. So the first way to think about this law of conservation of momentum is after two objects stick together and they crash. So imagine a car getting into a car accident. This is always a common example, and it crashes into another car, right? And those two objects move as one object. So the combined masses, so they're kind of think about them now as one mass together. All right, so now the momentum is sort of added together with this, and it kind of stays the same if they're moving in the same direction. So these two objects now that have been combined will now have a different velocity because the momentum is conserved and depends on mass and velocity. Okay, so those two cars that crash together, the momentum is conserved from the first car hitting the second car, but obviously the second car would slow the first car down because it has its own momentum, resulting in a different velocity. Okay, so because we're kind of adding mass, right? When these two cars collide, we're kind of adding mass. We're making essentially what was one car, separate car, right, and another separate car into one larger car. The velocity has to change too, right? Because if we have the formula P equals m times v, if you're changing this, that's going to result in a change of velocity too. But when two objects bounce off one another, momentum is transferred from one object to the next. So it goes from the first object to the second. So this is when, different from the first example of a car hitting another car and them sticking together, this one is where we have the second object moving and the first object stopping. Okay, so this causes them to move in different directions. We get to see that on the next slide in just a second. Okay, here, so continuing this, you can see this conservation of momentum in Newton's third law. So we think about Newton's third law, it's that every action, when an object hits another object or collides with another object, that object would move or respond with a force that's in equal and opposite direction. So because the action and reaction forces are equal and opposite, momentum is neither gained or lost. So this first object, as it rolls and hits the second object is going to roll with the same exact momentum as the first object did. Okay, so it's going to have an equal, and when I say opposite, now although this may move in the same direction, it's really pushing back on that first object as it collides. Okay, so the reaction force is seen here, right? So action and then reaction is when the second ball begins to roll. So here with this example, you can see this transfer of momentum. So this is a really classic example. You've got the pendulum swinging, and it's swinging. We call this the first object here, right? It's swinging and it's hitting the rest of the objects, all kind of touching, and the second object moves because that momentum is transferred from here through the other objects here to the second one, which would then swing up and then eventually swing back, right? Hit the balls again, and the first object would do that, and this would continue for quite a while. Similarly, if you have a ball here moving, if you have a ball here moving, this ball rolls, hits the second ball, now the second ball is going to move with the transfer of momentum from the first ball. Okay, so this next little concept map you're going to see is just a review going all the way back to section 1. It's not related to momentum, it's just sort of a review on falling objects and air resistance. So just try it. Try and put the words in the correct boxes and see if you can remember it. Thanks, and be ready for your quiz on momentum tomorrow. Write these terms here. You're starting with the overall idea of falling objects. So when falling objects fall, they reach something, and just take a second and do that. Okay, here are the answers to the review from section 1. Hope you enjoyed that and got some review on something that's been a little while since we talked about. Okay. Finally, I encourage you to check out this video. This has got some cool examples of momentum. And if you also want to try something fun, get a desk chair. Okay, so one of the chairs that has sort of wheels on the bottom, right, like this. It's got a chair like that. Okay, sit in the chair at home. Okay, stick your legs out, spin around, so go around in a circle. Then take your legs and put them crisscross in the middle, and notice how you speed up. I'll explain how momentum explains that in class tomorrow.